Okay, let's talk about ANN search. It's a really important technique when we're working with vector databases. Imagine you have a huge collection of images or text snippets. When you want to find something similar to your query, like a golden retriever, a traditional approach would be to compare a query against asterisk every single asterisk image in the database. That gets incredibly slow very quickly as the number of items grows. ANN search is all about speed. Instead of doing a perfect comparison, it builds an index almost like a map that lets it zoom in on likely candidates really fast. It's not always 100% accurate, but it's much, much faster than checking everything individually. Think of it as finding the closest neighbors without having to visit every single house. Okay, let's talk about how vector databases handle searches. When you want to find things that are exactly like your query, think of it like searching for an exact duplicate. That can be really slow, especially if the database is huge. It's like a full manual search through every single item. However, most of the time, we don't need perfect matches. Instead, we want to find things that are similar asterisk. That's where approximate vector search comes in. It sacrifices some precision for incredible speed and scalability. You trade off finding the absolute best result for getting results much faster. The trick is finding the right balance between how close you need your results to be and how quickly you need them. Okay, so building a really powerful vector search system isn't just about throwing some data into a database. It's all about creating a smooth pipeline that gets your text ready for the best possible results. First, we need to start with the raw information and make sure it's clean and prepped correctly. Then, you'll select an embedding model. Think of these as translators that turn words into numbers so the database can understand them. It's crucial to experiment with how you break your text into smaller pieces called chunks. A good chunk size allows for context while ensuring accuracy. Finally, we load those numerical representations into a vector database like Pinecone or ChromaDB. These are specialized databases built to handle similarity searches really well. Okay, let's talk about Phase. It's a really important library for working with vector databases. Basically, Phase helps you quickly find vectors that are similar to each other. It has different ways of organizing those vectors called index types. The simplest is the flat index, just like storing them in an array. That's fine for small amounts of data but gets slow fast as things get bigger. Then we have ifc, which breaks down the vectors into smaller pieces to save space and speed up searching. And finally, HNSW. This one builds a clever graph structure that makes it super efficient at finding similar vectors, especially when you're dealing with massive datasets. Let's talk about getting the most out of Phase. It's a fantastic tool for searching through vectors, but it can be resource intensive if not optimized correctly. One really important technique is centering your data, shifting everything so that its average value is 0. This makes searches much more accurate and surprisingly speeds up the indexing process too. Then there's subvector quantization, which lets you reduce the size of your index by focusing only on the most relevant parts of each embedding. Finally, compression techniques like product quantization can really shrink things down even further, though you might see a minor decrease in accuracy. The key takeaway: experiment with different approaches, then find what works best for your asterisk-specific data. Okay, let's talk about Facebook AI Similarity Search. It's a really important tool for working with vector databases. Basically, when you have tons of data represented as vectors, think images, texts, or even user profiles, finding similar items can be super slow without the right tools. Phase is designed to speed this up massively by utilizing GPU, those graphics cards that are great at doing lots of calculations at once. It builds an index to quickly locate which vectors are closest together and uses quantization techniques to make it even faster and more memory efficient, especially when dealing with huge amounts of data. Okay, let's talk about how you can really get the most out of Phase when dealing with a large number of vectors. It's fantastic at finding similar things, but sometimes we need to be more specific, like searching for only science-related results. Instead of trying to create super complicated indexes, the clever trick is to add extra information or metadata directly to each vector during its creation. Think of it like tagging each item with categories. Then, when you want to filter your search, Face lets you do it right at query time by specifying which category you're interested in. The example code shows how easy it is to add this metadata and then use the filter function during the search process. Okay, so we've got a lot of embeddings, right? Pinecone is great for handling them, but you don't want to just throw everything in and hope for the best. One key thing is chunking, breaking down large documents into smaller pieces. Think of it like organizing your bookshelf before searching. Also, adding metadata about each document like its type or source is super helpful for filtering your searches later on. Pinecone offers different index types to help you balance speed and accuracy, and if you're dealing with really huge datasets, vector quantization could be an option, but it's a more advanced technique. Let's talk about how Pinecone makes scaling your vector search super easy. The key is their pod-based architecture. Imagine little independent databases working together as a cluster. Each pod can handle data and queries on its own, so if one pod goes down, the others keep going. You can add more pods to that cluster as you need more capacity, and it's all done automatically without any downtime or complicated migrations. It's really designed to grow with your needs. Okay, let's talk about taking our vector searches even further with Pinecone. We've already seen how to use embeddings for semantic similarity. Now, we can add another layer of control through metadata filtering. Think of it like adding labels to each item in your index category, brand, price, whatever makes sense for your data. Pinecone lets you associate key value pairs called metadata with each vector. This allows us to target our searches incredibly precisely. For example, we can filter results to only include electronics from Samsung. And the really cool part? We can combine this metadata filtering with a regular vector similarity search, a hybrid query. This gives us the power of both semantic understanding and targeted precision. Okay, let's talk about Weave8. It's a really cool open source vector database that's becoming increasingly popular for building AI applications. Unlike traditional databases, Weave8 is built around the concept of vector-first data modeling. That means you represent your data as embeddings, essentially numerical fingerprints of meaning. These embeddings are created by feeding text or other data into embedding models like OpenAI. It handles things at a semantic level, so searching based on meaning instead of exact matches, making it super useful for things like recommendation systems and similarity search. Okay, so let's get a Weave8 instance up and running. This slide shows you how to access it using both our REST file and GraphQL API. REST is really simple. Think standard HTTP requests like GET or POST and CREATE for scripting and basic integrations. You can add data directly with a call command. On the other hand, GraphQL gives you more control. It lets you specifically ask for only the information you need, which is super helpful when dealing with complex searches or large amounts of data. You'll find detailed examples in the Weave8 documentation if you want to dive deeper. Okay, let's talk about how Weave8 makes it really easy to connect your vector database to some of the coolest AI models out there. We've got modules specifically designed for OpenAI, Cohere, and even Hugging Face transformers. This means you can quickly generate embeddings, essentially numerical representations of your data using these powerful language models. It's a fantastic way to boost the accuracy and relevance of your searches. Think of it as building a bridge between Weave8 and your favorite AI tools. Let's talk about how Vespa AI makes semantic search happen in enterprise AI. Essentially, it's all about understanding meaning rather than just matching keywords. We first turn our data, think documents, images, into numerical representations called embeddings. These embeddings capture the core ideas within each piece of content. Then we store these embeddings in a specialized vector database that Vespa manages, designed to be incredibly fast and handle massive amounts of information. When someone searches, their query is also converted into an embedding, and Vespa quickly finds the data embeddings most similar, meaning most relevant to the user's search terms. It's like finding the closest match based on understanding, not just literal words. Vespa takes care of everything from creating those embeddings to storing them in the database and running the search itself, making it a really streamlined solution for large-scale AI applications. Okay, so when we're building AI search applications using Vespa, it all starts with structuring our data effectively. We'll need a vector field to store the numerical representation of our text. Basically has similar different pieces of content to each other. Alongside that, we want to keep the original text itself, often broken down into fields like title and body. And lastly, let's add some metadata, things like author or category, to help us filter and sort our results. Let's talk about Milvus. It's an open source vector database that's becoming seriously important for AI. Basically, it's like a supercharged index specifically designed to handle those complex numerical representations or vectors of your data. Think of it as the engine behind finding similar things quickly. Milvus is built with scalability in mind, meaning it can grow with your needs and even run across multiple computers. It's also really well suited for cloud environments, making deployment straightforward. And because it's open source, you have a lot of flexibility to tweak it exactly how you need it, which is fantastic. Okay, let's talk about scaling your Milvus cluster and how distributed indexing plays a key role. Basically, as your data grows, you'll want to move beyond a single node. Milvus uses something called sharding. Think of it like splitting your data across multiple servers to handle the increased load and speed up queries. Replication is also important. Creating backups on different nodes ensures that if one server goes down, you still have access to your data. Distributed indexing, particularly HNSW, allows Milvus to efficiently search across these shards, making similarity searches much faster for large datasets. We'll explore some scaling strategies like adding more nodes and tweaking index parameters. It's all about finding the right balance between performance and resources. And don't forget about using Milvus's different node roles to manage everything effectively. Got questions? Check out the official documentation for deeper dives. Okay, let's dive into comparing Milvus, Face, and Annoy, three popular choices for working with vector embeddings. First up is Face, developed by Facebook. It's known for being incredibly fast and able to handle massive datasets, but it can be a bit of a memory hog. You really need a lot of RAM. Annoy takes a slightly different approach, building a tree structure that offers a good balance between speed and memory usage. Incremental updates make them easier to maintain if your data changes frequently. Finally, there's Milvus. This is a full-fledged distributed system designed for large-scale vector storage and search, making it great when you need to scale across multiple machines. Let's dive into Qdrant, a really cool vector database. Think of it as a super fast way to find similar things like images, text, or anything you can represent as a numerical vector. What makes Qdrant stand out is its real-time indexing. That means when new data comes in, the system updates almost instantly, so your searches always have the latest information. It uses clever algorithms to quickly narrow down the possibilities and give you what you're looking for, even with huge amounts of data. Okay, let's dive into how we can combine Qdrant with Python, FastAPI, and LangChain to create really smart search. First, we'll need to set up our environment by installing the necessary packages: Qdrant client, FastAPI, UVic on our server, and LangChain. Then we will build a simple API endpoint using FastAPI that takes text as input, turns it into embeddings using LangChain's embedding model, stores those embeddings in Qdrant, and finally returns relevant search results. LangChain's vector store index creator will be key to building indexes based on the Qdrant database. Okay, let's talk about how LangChain makes working with vector databases a whole lot easier. Essentially, it creates an abstraction layer. Think of it as a translator that lets you use different vector stores without rewriting your entire code every time you switch. The base vector store defines the core operations you'd expect from any vector database, and then we have actual implementations like ChromaDB or Pycon which are called vector stores. LangChain chains leverage this abstraction to seamlessly fetch relevant embeddings when needed for things like question answering. This means you get flexibility, less code to write, and a codebase that's much easier to keep tidy. Okay, let's talk about how we store those all-important vector embeddings when building RAG systems. Basically, you've got a few main options. You can use dedicated vector databases like Pinecone or ChromaDB. These are specifically designed for really fast similarity searches. Alternatively, you might choose a hybrid approach where your embeddings live alongside other data in a traditional database like PostgreSQL. And if you're dealing with very large documents, chunking them up and embedding each piece individually can be beneficial. When deciding on your strategy, think about things like how well it will scale as your data grows, what the cost is going to be, and most importantly, how quickly it can index and find relevant information. HNSW indexing is often a good choice for speed. Okay, so let's talk about keeping those embeddings fresh in production. It's not enough just to build them once, you need a plan for updates. We recommend scheduling regular re-embedding processes, think daily or weekly depending on how often your data changes. Also, instead of rebuilding the whole database every time, try incremental updates. That means only incorporating new content or modifications. Versioning embeddings can be helpful too, especially if you're experimenting with different versions and want a way to roll back if something goes wrong. And crucially, always monitor your search results after any update. Track things like accuracy and user feedback. It's the best way to know if the changes are truly beneficial. Okay, so let's talk about a really important challenge when using vector databases, embedding drift. Basically, the numerical representations of your data, those embeddings, can slowly change over time. This happens because things evolve, and what used to be similar might not be anymore. There are several reasons for this, like changes in the actual data itself or even just the model learning differently as it gets older. The good news is there are ways to tackle it. You can retrain your embedding model regularly with fresh data, use a sliding window approach that only looks at recent data, or dynamically update your index. And crucially, you need to monitor how well your searches are performing. If you see a drop in accuracy, it's time to take action. Okay, let's talk about keeping your vector database reliable. As you add more data and use it more, making sure everything stays consistent is super important. We have a few key strategies to think about. Replication means having copies of the index spread out in different places, so if one goes down, we don't lose all our information. Quorum rights ensure that updates are only considered successful after a certain number of nodes agree on them. Then there's durability. Snapshots and backups let us roll back to a previous state if something goes wrong, and using immutable indexes, structures that can't be changed once created, helps prevent accidental data loss. Combining these approaches will give you the most solid foundation for your vector search. Okay, let's talk about taking search to the next level. Traditionally, we've been really focused on searching with words text. But what if you could find pictures that look like something you described, or music that feels like a certain mood? That's where multimodal search comes in. It's all about representing different kinds of data like images, audio, and text as numerical vectors called embeddings. Think of it like this: an embedding is a fingerprint for each piece of content. The closer the fingerprints are to each other, the more similar they are in meaning. So, if you ask for a sunny beach, the system generates an embedding for that prompt and then searches a vector database for images and audio clips with similar embeddings, effectively finding visuals and sounds that capture the same essence. Okay, so as we're scaling up with vector databases, and let's be honest, the asterisk need asterisk to scale. We can't just throw everything onto one giant server. That's where sharding comes in. Think of it like dividing a really big spreadsheet into smaller, more manageable sections that each live on its own computer. This makes searching faster because the database can process those smaller chunks simultaneously. Then, load balancing ensures that all the queries are spread out evenly across these shards, so no single shard gets overloaded and everyone's happy. We use techniques like consistent hashing to make this really efficient when we add or remove nodes from our system. Ultimately, sharding and load balancing are key to making vector databases powerful and scalable. Let's talk about using vector databases for time series and log data. Think of it like this: instead of looking for specific keywords or patterns, which can be really tricky with complex data, we convert everything into a numerical representation, almost like a secret code. This code captures the meaning behind the data, whether that's server performance metrics or entries in a log file. We store these codes in a special database designed to quickly find similar ones. When something new comes through, we encode it and search for the closest matches. Any significant differences, those are the anomalies that need our attention. It's a much smarter way to detect problems and opportunities. Okay, let's talk about how embedding search can supercharge your personalization engines. Basically, we're moving beyond simple keyword matches and diving into understanding the asterisk meaning asterisk behind what users are looking for or interacting with. First, we create embeddings, which are like unique fingerprints representing the meaning of each item, whether it's a product, an article, or anything else. Then, these embeddings are stored in a special database called a vector database, allowing us to quickly find items that are conceptually similar. When someone interacts with your system, we run a search against this database, using similarity scores to rank the results. This opens up huge possibilities for personalization. Think smarter product recommendations, more relevant content feeds, and even improved search accuracy by taking context into account. Okay, let's talk about keeping things speedy when your app gets really popular. You've probably heard that vector databases are great for searching similar items like images or text. But if you have a lot of users, the first time someone searches, it can take a while for the database to figure out what those similarities are. That's because the database hasn't warmed up yet. It needs to do some calculations to create those embeddings which represent how similar things are. So, we need tricks to get things going quickly. We can pre-calculate embeddings for items that people often look for, or send a bunch of requests together at once. A proxy layer can also help by caching the results before they hit the database, and we can even schedule regular updates for less popular data. Basically, it's all about making sure your search is fast and responsive. Happy users. Okay, so we're tackling a really common challenge. Your data isn't all in one place. It might be scattered across different databases. Maybe you have customer information in PostgreSQL, product details in MongoDB, and logs in Elasticsearch. Building a unified search experience means we need to connect these silos. The first step is generating embeddings for each piece of data using the same model. Then, instead of just relying on one vector database, we can build indexes that actually span multiple databases. Think about how you could index metadata alongside your vectors. Finally, a query routing system becomes crucial. It needs to figure out which database holds the most relevant information and combine those results for a complete answer. Okay, so imagine you're building a really smart chatbot. For a long time, getting the right information to answer questions was tricky. It involved separate searches and then trying to piece things together. But vector databases are making this much easier. They let us represent both your documents and user questions as numbers, essentially creating a map of their meaning. This way, we can find the most relevant documents instantly without relying on exact keyword matches. It's like searching by idea instead of word. Let's talk about how the distance metric you choose can really impact your embedding search results. It's not a one-size-fits-all situation. Cosine similarity is great for comparing text, focusing on how similar things are, rather than just how much asterisk. Euclidean distance, on the other hand, looks at the straight line difference between vectors, so it's really good for images where intensity matters. Dot product is useful when you have specific weights assigned to different features, like saying a certain word in a review is twice as important as another. Think about your data, how those features are scaled, and what you're trying to find. That will help you pick the right metric. Okay, let's talk about how we can make those massive vector databases a little less gigantic. We're tackling memory usage, and one really useful technique is called quantization. Think of it like this. We want to represent our data embeddings with fewer bits without sacrificing too much accuracy. There are several ways to do this, from simply scaling the numbers down to grouping similar vectors together, or even converting them to just -101. Product quantization is a powerful method that breaks a vector into smaller parts and quantizes each part separately. It's all about clever compression, reducing the size of those embeddings so we can store more data in our databases without blowing up our memory. Okay, so embedding search is great, but sometimes you get a ton of irrelevant results. That's where pre- and post-filtering come in. First, let's think about pre-asterisk filtering before we even generate the embeddings. We can refine the user's query by adding synonyms or related terms to broaden what gets considered. Or, if your data has good metadata like categories or tags, filtering based on the asterisk before asterisk embedding generation is a huge time saver. Finally, domain-specific filters, where you leverage subject matter expertise to narrow things down even further. Now, on to post-filtering once we've got our embeddings. Instead of just using the raw similarity scores, adjust those thresholds to better match your application's needs. You can also combine embedding similarity with metadata relevance, essentially boosting results that align well with specific categories. And don't be afraid to filter out any embeddings that still seem a little off, even after all that. Okay, so we're diving into how to build really fast search systems that can handle new information as it comes in. It's essentially a continuous loop. You get some new data, say a blog post or an image description, and the first step is transforming it into a numerical representation called an embedding. Think of it like creating a fingerprint for the data. This happens at the same time as we receive the original data. Then we need to store those fingerprints in a vector database which is specifically designed for quickly finding similar things. And finally, when someone searches, we create an embedding for their query and use that to find the most relevant items from our database. The trick is making each part of this process as fast as possible, like processing data in batches or using models that generate embeddings really quickly. Okay, let's talk about bringing vector databases into your existing data infrastructure. You've probably got a massive data lake or warehouse, a fantastic starting point. But searching through all that data can be slow and ineffective if you're just looking for things that are similar in meaning. That's where vector databases come in. They let you represent everything as numbers, essentially vectors, so you can search based on how close those vectors are to each other. Think of it like finding similar colors. You wouldn't compare pixel values directly, would you? We build a pipeline to get our data from the lake or warehouse into these vector embeddings and then load them into the database for super fast similarity searches. It's about connecting the dots between your structured and unstructured information, making it easier to uncover insights. Okay, let's talk about scaling your vector search beyond a single cloud provider. Multi-cloud setups offer benefits like increased reliability and avoiding being tied to one vendor's ecosystem. The key is strategic architecture. We need to think about replicating our data across different clouds, for example, using Pinecone alongside something like AWS Kendra. A routing layer is also crucial. It's essentially an API gateway that directs queries to the vector stored that will give you the best results at any given time. And finally, keeping your metadata consistent across all these platforms is really important, so we often use change data capture tools to ensure everything stays in sync. Okay, let's talk about keeping your vector data safe. It's surprisingly complex. Because we're dealing with embeddings that represent information, understanding where this data lives is key. You need to be aware of things like GDPR and other data protection rules, and make sure you're storing everything in the right place. Think about access to, who needs to see or change these vectors. And don't forget encryption, both when the data is sitting idle and when it's being moved around. Finally, if you're using a service provider, dig into their security practices and make sure they've been checked out by experts. Okay, let's talk about picking the right embedding model for your AI project, especially if you're working in a specific area. It's not enough to just use any general purpose model. You need something that really understands your data. We want to look at things like how relevant the model is to your domain, its size. Bigger models can be more accurate, but also require more computing power and even the dimension of the embeddings themselves. Then we need a solid way to test them out, which often involves creating a data set that reflects your specific needs. using metrics like recall at k to see how well it finds relevant information, and then iteratively tweaking things until you get the best results. Okay, let's talk about keeping track of those embeddings. Think of them like fingerprints for your data. They are what allow your AI to understand things. But as models improve and change, so do the embeddings. If you don't manage these versions properly, it can really mess with your system's performance, leading to unexpected results. We want to make sure we have a way to roll back if something goes wrong, or to compare how different versions are performing. There are several strategies vector databases that automatically handle versioning, adding detailed metadata like the model name and training date, taking regular snapshots of your embeddings, and continuously monitoring performance to spot any regressions. It's all about keeping things consistent and reliable for your AI applications. Let's talk about how vector databases are revolutionizing the way we search through massive amounts of information in specialized fields. Traditionally, searching relied on exact keyword matches, but that's often not enough when dealing with complex documents like medical records, legal contracts, or financial reports. Vector databases and embedding technology provide a huge leap forward. Basically, they convert these lengthy documents into numerical representations. We call them embeddings that capture the asterisk, meaning asterisk of each section. So if you're searching for information about chest pain, the database can find related sections even if those sections don't explicitly use the word pain. It's all about understanding context and relationships, which makes it incredibly powerful for areas where precision is critical. Okay, let's talk about how to handle latency when using really powerful semantic search API. The big thing is that latency isn't just one number. It's the total time it takes for a request to go out and come back in. As your data gets bigger and more complex, each step like creating those vector representations, keeping the index updated, or comparing vectors adds delay. Think about how long it takes to make an embedding, how quickly you can build that index, and then when someone actually asks a question, how long it takes for the system to find the best matches. Different applications have different expectations too. A chatbot needs super fast responses, while something like e-commerce search can tolerate a little more delay. So, figuring out your latency targets is really important. What's acceptable for your users, and where do you need to focus your efforts on making things faster? Okay, so we're tackling the problem of how to make search smarter. Traditional keyword searches are often frustrating because they don't understand what you asterisk mean asterisk. To fix this, we use embeddings, basically a way to represent text as numbers that capture its meaning. Think of it like assigning each piece of text a unique fingerprint based on its content. We then store these fingerprints in a special database designed for quick searching, called a vector database. When someone asks a question, we convert their question into a similar fingerprint and use the database to find the most relevant pieces of information, those with the closest fingerprints. It's all about finding things that asterisk mean asterisk the same thing, even if they don't use the exact same words. And finally, it's important to be able to explain asterisk why asterisk a particular result was shown, so users can understand and refine their searches. Okay, let's talk about getting your vector database running in the real world. Deploying it effectively often means thinking about where you need it most. Serverless environments like AWS Lambda or Azure Functions are fantastic for handling those incoming queries. They automatically scale up where needed and only charge you for what you use. It's a really cost-effective way to do things. However, if low latency is critical, like on a mobile app, you might want to consider edge deployment. That means running the vector search model right on the device itself. Think of it as bringing the database closer to your users for super fast responses, even without an internet connection. Okay, let's talk about keeping an eye on your vector database and embedding search tools. It's not enough just to build them, you need to ensure they're running reliably. Essentially, we want to make sure our system is always available and performing quickly. That means tracking things like uptime, aiming for nearly perfect availability, monitoring the health of the database itself, looking for errors or resource issues, and paying close attention to query latency, how long it takes to get search results. Finally, You can also monitor recall and precision if you want a deeper understanding of how well your embeddings are capturing relevant information, all while setting up alerts so you're notified immediately if anything goes wrong. Okay, let's talk about keeping your embedding data safe and secure. Think of embedding stores as incredibly powerful tools, but like any tool, they need proper oversight. We really need to think about who owns the embeddings. Is it your team or a provider? Then we need to create clear access levels so only the right people can see and modify the data. It's also important to track which models are being used and how they're performing, as well as having policies in place for how long the data is stored. There are several ways to manage this, things like role-based access control, where you assign users to specific groups with permissions, or attribute-based access control, which lets you define rules based on user characteristics and environmental factors. Okay, let's talk about vector databases. You know how traditional databases work. They are great for storing things like customer names and addresses. But what do you do when your data isn't structured in a simple table? Think of images, long text passages, or even music. Vector databases are designed to handle that kind of data. They store information as vectors, which are just numbers representing the content. These vectors allow us to find things that are similar, like finding an image that looks like another one, or a piece of text with a related meaning without needing exact keyword matches. It's a game changer for all sorts of applications, especially when working with AI and creative projects. Okay, let's dive into the top 5 vector databases that are really shaping how we're building AI applications in 2025. First up is Pinecone. It's a managed service, so it takes care of all the heavy lifting for you and is perfect if you're looking to get something deployed quickly at scale. Next, Weave stands out as an open-source semantic search engine, allowing you to work with complex data structures in a really intuitive way. Then there's Milvus, built for massive datasets and designed to handle high performance. ChromaDB is fantastic for getting started and experimenting because it's lightweight and super easy to use. Finally, Qdrant offers speed and efficiency through its distributed architecture and Rust implementation. Keep in mind that the field is constantly changing, so always do your research to find the best fit for your specific project. Okay, let's talk about embeddings. Think of them as a way to translate words and sentences into numbers, really sophisticated numbers that represent their meaning. Word2Vec was an early breakthrough. It showed us how similar words could have similar numerical representations based on the context they appeared in. But modern AI, especially transformer models like BERT, are taking this much further. They create embeddings that capture incredibly nuanced meanings and relationships between text. Essentially, we feed our text to these models and they spit out a vector list of numbers which tells us how closely related the text is to other texts in our database. Let's talk about building a smarter search system. We're going to explore pgvector, an extension for PostgreSQL that lets you store and quickly find similar text using vector embeddings. Think of it as adding a super fast index specifically designed for understanding the meaning behind words, not just matching them. Essentially, we'll transform our text data into numerical representations vectors and then use those vectors to efficiently find related content in our database. It's a game changer for semantic search. Let's talk about building really smart search applications using Amazon Titan embeddings. Titan offers a super convenient way to generate vector embeddings. Essentially, they're like fingerprints for your text data, capturing its meaning. These embeddings are then stored in a vector database, and when someone searches, their query gets turned into an embedding too. The system quickly finds the most similar content based on these numerical representations, giving you incredibly relevant results without needing to manage servers or worry about scaling. Let's talk about how Azure Document Intelligence can revolutionize the way you work with documents. Basically, it's like a super smart assistant that automatically understands what's inside PDF, Word files, and other unstructured formats. It doesn't just see images of text, it actually converts them into readable data. Then it goes through identifying key pieces of information, things like names, addresses, and dates, and even figures out how those elements relate to each other. Finally, it extracts the most important phrases that tell you what a document is about. This whole process happens automatically, then DPI plugs right into Azure Cognitive Search, making it super easy to build really powerful search tools based on your documents. Okay, let's talk about choosing the right vector database. We have three main contenders: Veis, Milvus, and Pinecone. Veis is a really popular choice for smaller projects because it's super fast on your CPU, but it doesn't scale very well to massive datasets. Milvus, on the other hand, is designed to be a distributed system, so it can handle huge amounts of data and offers great availability. And then there's Pinecone. It's completely managed by them, which means you don't have to worry about any infrastructure at all. It integrates seamlessly with your machine learning workflows. Think about how big your dataset is, what kind of performance you need, and whether you want to handle the complexity of managing a database yourself. Those are really important questions when making your decision. Okay, so let's talk about how vector databases and embedding search are making AI smarter. Traditionally, when you search for something online, it relied on matching keywords directly. But that can be really limiting, like if you asked what's a good Italian restaurant near me, and the engine only found restaurants with those exact words in their description. Vector search is different. It transforms everything: text, images, even audio, into numerical representations called embeddings. These embeddings capture the essence of the data. A vector database then stores these embeddings, allowing it to quickly find similar things. It's like creating a map where each item is represented by its location. When you ask a question, it's converted into an embedding too, and the system finds all the other embeddings that are closest, revealing truly relevant information. It's really powerful because it understands meaning instead of just matching words. Okay, so we're diving into a really cool combination here. We'll be using LangChain, which is like the glue that holds together lots of AI tools, and pgvect. This is a way to store vector embeddings in your PostgreSQL database. Basically, we are building an intelligent search system. LangChain lets us easily connect these components, and pgvector gives us a solid place to keep all those numerical representations of our data. This means instead of just searching for keywords, the AI can understand what you're asking about. It's like giving your LLM direct access to relevant knowledge stored in a structured way. The main advantage? Super fast retrieval and more accurate results. Okay, let's talk about deploying a powerful vector search system using Milvus. Milvus is basically like a super fast database for finding similar things. Think of it as searching for images that look alike or documents with similar themes. To make this really useful, we need to get it running in a robust way. We'll start by setting up our infrastructure, likely using Kubernetes or cloud services to manage everything neatly. Then, we deploy Milvus itself, making sure it's replicated and sharded so it can handle lots of data and stay reliable. We connect it all together with an API gateway that's like a front door for your application, and finally, we index our data into Milvus using embedding models, creating the search endpoint you can actually use. Okay, so when we're dealing with vector databases and searching through tons of data, speed is everything . Different indexing methods help us achieve that. HNSW is like a really efficient map. It quickly finds the closest vectors without checking every single one. IVF uses a clever system to narrow down potential matches, making it super fast but sometimes sacrificing a bit of accuracy. And then there's the simple flat index, which is great for smaller data sets but becomes incredibly slow as your data grows. Okay, let's talk about embedding search. It's a really exciting way to find information that goes beyond simple keyword matches. Basically, instead of looking for exact words, we're capturing the meaning behind them. We do this by creating something called embeddings, which are just numbers representing data like text or images. These numbers allow us to measure how similar different pieces of content actually are. A vector database is then used to store and quickly search these numerical representations. You can use it for all sorts of things: recommending products that share a similar concept, building chatbots that understand what people mean instead of just what they type, or even discovering related articles. There are some fantastic tools out there like Pinecone, ChromaDB, and Weaviate to help you get started. Okay, let's get started with Qdrant. We're going to walk through a super quick setup so you can start experimenting with real-time vector search. First, we need to install the Qdrant client library using pip. It's really simple. Then we connect to the database, which is typically running on localhost at port 6300. Next, we create an index. This tells Qdrant how to efficiently store and search your vectors. After that, we add some data by providing vector embeddings along with any relevant metadata. Finally, we can query the index to find similar items based on a given query. It's a really powerful tool for semantic searching. Okay, let's talk about RAG. It's a really cool technique that combines the power of large language models with the speed of vector databases. Basically, first we turn our text like your questions or documents into numerical representations called embeddings. Think of it like giving each piece of text a unique fingerprint based on its meaning. These fingerprints are then stored in a special database built for searching these numerical fingerprints really efficiently. When you ask a question, we convert that into a fingerprint and the vector database instantly finds the most similar pieces of information. Finally, the language model like ChatGPT or Bard uses this relevant context to generate a much better answer than if it were working alone. Okay, let's talk about speeding up those amazing AI apps. A big problem is that calculating embedding those numerical representations of text or images can be really slow, especially when you have to do it over and over again for every single search. That's where caching comes in. Think of it like a really fast shortcut. We start with a super quick in-memory cache, basically holding the most frequently asked for embeddings right there. Then we might use an intermediate cache, which is a bit slower but holds more data. And finally, for even bigger datasets, a long-term or hybrid approach that combines different storage methods. The goal is always to avoid recomputing those embeddings every single time, leading to much faster response times and happier users. Okay, so we're building a search system that can handle different types of data, text, images, and even audio. The key is to create embeddings, which are basically numerical fingerprints of each piece of content. It's like giving every document or image a secret code based on its meaning. We use models like BERT for text, CNN for images, and specialized audio models to generate these codes. Then, we store everything in a special database called a vector database that's designed to quickly find similar codes. Finally, when someone asks a question, we turn their query into an embedding too and let the database do its magic, finding the most relevant content based on similarity. Okay, so scaling a vector database is all about making it handle more data and requests without slowing down. First, we build a cluster, basically a team of nodes working together for redundancy and speed. Then we use sharding to split the data into smaller pieces, spread across different nodes. Think of it like dividing a giant puzzle into many easier to manage sections. Finally, replication creates copies of the data on multiple nodes, so if one fails, you still have others ready to go. It's not just about adding more computers, it's about organizing your database smartly for optimal performance and reliability. Okay, let's talk about keeping your searches super current. Think about how quickly things change. A news article gets updated, a product description changes, or a customer leaves a review. Traditional search indexes can't always keep up with that speed. Vector databases and embedding search tools are designed to solve this. Basically, whenever new data comes in, we immediately convert it into a numerical representation and embedding that captures its meaning. Then, we add those embeddings directly to the index, so your searches instantly reflect the latest information. Many systems even prioritize more recent updates, giving you the most relevant results possible in real time. Okay, let's dive into some fantastic open source options for vector search. First up is ChromaDB. It's incredibly easy to get started with, perfect for quickly testing out your ideas. Then we have Milvus, which is designed to handle larger datasets and scales really well, making it ideal for production deployments. Qdrant is known for its speed and efficiency, especially when dealing with dense vectors. Weave stands out because it's a graph database that seamlessly integrates vector search, brilliant for knowledge graphs. Finally, Vespa is a powerhouse built to handle massive datasets and complex ranking scenarios. Okay, let's talk about how we used to search the web versus how we're doing it now. Traditionally, when you typed something into a search box, computers looked for exact matches between your query and the words in each web page. That's called lexical search. It's fast, but it can miss things because it doesn't understand asterisk meaning asterisk. Now, with vector databases and embedding search, we do things differently. Instead of matching words, we represent everything your search terms and the documents themselves as numbers, creating a vector. These vectors capture the underlying meaning. So, searching for comfortable running shoes might return different athletic shoes than just finding pages that contain the exact phrase red shoes. It's about understanding what you really want, not just what you typed. Okay, let's dive into how we manage our embeddings in vector databases. It's not just about adding new stuff, it's about keeping everything organized and accurate. Versioning is key. Think of it like saving different drafts of your data. When you update your model or your source data, you're creating a new set of embeddings. Tracking these versions lets you go back if something goes wrong, compare how different models perform, and make sure you can always reproduce your result. Then we have updates. Sometimes you want to do a full rebuild with the latest model, but often incremental updates are better, only updating what's changed. Finally, deleting old or irrelevant embeddings is super important. It prevents our databases from growing endlessly and keeps search speed snappy. We usually archive older versions and set up a regular process for purging data that's no longer needed. Okay, let's talk about how you can actually use vector search with the databases you probably already know and love, like SQL and NoSQL. It's not about throwing everything away, it's about adding a really powerful new layer. Basically, you'll embed your existing data using an embedding model. Think of it as turning text or images into numerical representations. Then, those embeddings are stored in a vector database alongside links back to the original data in your SQL or NoSQL database. When someone searches, their query gets embedded too, and the vector database finds similar vectors. Finally, we pull the actual records from your existing databases based on how close those vectors are. It's a smart way to supercharge your search capabilities without needing a huge rewrite. Okay, let's talk about where vector search is headed in the business world. It's really exciting stuff. We're seeing vector databases get much better at handling huge amounts of data. Basically, they can find things based on meaning rather than just matching words. The trend is definitely towards combining traditional keyword searches with this new meaning-based approach. Also, generative AI models are going to rely heavily on these vector stores for context. And, get this, we'll see systems that automatically update the information used to build those vectors so your search results stay up to date. Finally, data privacy is a big deal, and federated vector search will let companies search across their own data without having to move everything around. Okay, let's talk about picking the right vector search tool for your AI project. It's a really important step, and it goes way beyond just finding something fast. You need to think carefully about how much data you're dealing with. Is it a small collection or a massive data set? Then, make sure the tool works seamlessly with the embedding model you've chosen. Don't forget to consider things like how quickly you need results, query latency, and whether the tool can actually scale as your project grows. And of course, cost plays a big role too. It's important to understand all the pricing structures involved. Okay, let's talk about embedding drift. It's a really important concept to understand when you're using vector databases and embedding search. Basically, over time, the vectors that your model generates as numerical representations of text or images can start to become less similar to new data. It's like your model is gradually forgetting what things look like as it sees more and more information. This often happens because language changes, user behavior shifts, or even when you retrain your model, you can inadvertently introduce drift. Recognizing this drift early on allows you to take steps to mitigate its impact. Okay, let's talk about RAG retrieval augmented generation. It's a really clever way to make large language models even better. Basically, RAG combines an LLM with something called a vector database. First, we turn your text into numerical embeddings, which are like fingerprints of the meaning of that text. These embeddings are then stored in this special database that allows us to quickly find similar pieces of information later on. When you ask a question, the system creates its own embedding for your query and searches the vector database for the most relevant context. Then the LLM uses both its existing knowledge asterisk and asterisk that retrieved context to give you a super informed answer. It's like giving the LLM a really helpful cheat sheet. Okay, so let's get serious about how we actually know if our vector databases are doing a good job. It's not enough to just plug them in and hope for the best. We need to measure things. There are a few key metrics like precision at K, which tells us how many of the top results are truly relevant. Then there's recall at K, which measures how much of the good stuff we actually found. And we also have NDCG, which takes ranking into account. Finally, don't forget query latency. How fast does it take to get a response? To help us with this, we can use synthetic benchmarks, basically creating our own test data and questions. Or, even better, testing against real-world data from how people actually use the system. And many of these tools already provide metrics on their internal performance too, so keep an eye out for those. Benchmarking is something you'll want to do regularly as your data changes. Okay, let's talk about scaling your vector database strategy. We're looking at how to deploy it across multiple cloud providers like AWS, Google Cloud, and Azure, each with their own strengths. Serverless functions are a huge part of this too. They can automatically index new data, handle search requests, and scale up or down as needed based on demand. Think about where your data needs to be located for optimal performance and how to avoid being locked into one specific vendor. Let's talk about how embedding search is revolutionizing product discovery in e-commerce. Traditionally, when you searched for something on an online store, it relied mostly on matching keywords directly. But that often meant users missed products that were relevant but didn't use the exact same words. Embedding search changes all of that by representing both your product descriptions and your searches as numerical vectors, basically capturing their asterisk meaning asterisk. Think of it like this: instead of just looking for red shoes, the system understands you might also be interested in crimson sneakers. This leads to more relevant results, a better user experience, and opens up exciting possibilities for personalized recommendations. Okay, let's talk about keeping your sensitive information safe when using vector databases. It's more than just creating the embeddings. You need a solid security plan in place. Think of it like building a fortress around your data. First, consider masking and tokenizing, essentially hiding parts of the data within the embeddings themselves to reduce risk. Next, control who has access with strict permissions using something called role-based access control. Don't forget encryption both while the data is at rest on the server and when it's traveling around. And finally, regularly check for any suspicious activity or breaches through audits and monitoring. Finally, make sure you align your approach with regulations like GDPR, HIPAA, and CCPA to ensure you're meeting all legal requirements. Let's talk about how vector databases are revolutionizing search. Instead of just looking for exact matches like with traditional keyword searches, these databases understand the asterisk meaning asterisk behind your data. They do this by turning things, videos, audio files, even images, into numerical vectors that represent their essence. This opens up incredible possibilities. Imagine searching for a video based on a specific scene, finding music tracks just by hearing a similar sound effect, or instantly locating visually similar images. It's all about semantic search, understanding what something asterisk is asterisk, not just what it's asterisk called asterisk. Okay, let's dive into building a really smart search system. The foundation of this setup is using OpenAI powerful embeddings. They transform text into numerical representations that capture the asterisk meaning asterisk behind the words. We then store these vectors in a vector database like Pinecone or Chroma, which is optimized for quickly finding similar items. Think of it as a super efficient way to compare ideas instead of just looking for exact matches. Finally, we need an interface where users can type in their queries and get results. The system compares the queries embedding with all the existing ones in the database and returns the closest matches. Thank you for watching.